Assalamu alaikum dear students. Today our lecture is about behavior of contaminants in soil. Previously we talked about the basic phenomena of sorption and desorption, and this phenomena was actually related with the ability of any kind of solute which has entered into the soil volume, and we were interested to know what kind of behavior it is going to obtain, what kind of behavior it is going to present. So it all depends upon, first of all, the solute and its characteristics, and secondly, the nature of the soil, how the soil is going to behave for that particular solute which has entered. So furthermore, in this lecture, we will also talk about the sources of contamination, from where the contamination is approaching the soil volumes. So it is important because we must know the quantity and the continuity of the source. So how long it will persist and how it is going to get absorbed in our soil volumes. So all these phenomena will be discussed, and we will try to understand how sorption and desorption processes are actually exhibited in the soil volumes. Before going into that, before going into the details of these phenomena, there is another important factor which you will understand today. It is about the concentrations of different solutes which are already present in the soil volume. For example, we take the example of our water sample, which can be from any source like surface water or groundwater. So, from both the sources, the water is not purely H2O, which is called distilled water, but it is also containing some other minerals. It is also containing some other inorganic compounds. It is also containing some other organic compounds. Maybe some heavy metals are also present in the water which we are testing. So the water is containing some calcium ions, some sodium ions, some potassium ions, some magnesium ions, some chloride ions, and then it is also having some sulfates, some nitrates. So it is a mixture of all these things which are present in our water sample. So these are the basic ingredients required for any usage of water, whether it is for drinking purpose or it's for agriculture purpose. So it is the basic requirement. So a typical water sample is actually having all kinds of uh, such parameters which have entered into that water sample. So similarly, the soil is also having similar concentrations of some of the solutes which have entered into the soil through some other sources, or it is already existing in that soil volume uh, and naturally. So it is based on its rock formations. Some rock fragments will be there, maybe uh, some already existing minerals are there which will be a part of their volume. So similarly, all these solutes, which can be minerals, which can be heavy metals, which can be organic or inorganic in nature, so everything will be present in the soil, but we are not going to declare that soil contaminated until and unless that concentration exceeds a particular limit, and that particular limit has been defined by environmental protection agency standards, EPA standards. US EPA standards have been prepared to properly demonstrate what will be actually called a contaminated site, contaminated soil sample. And similar is the case with the water as well. So unless we have the concentrations exceeding the permissible limit, we will not declare it as the contaminated source. So this is something about the uh, soil and its contamination. So there are some particular limits which will be defined. So for example, metals like aluminium, uh, so on an average it will be having a range of 71,000 milligram per kg. So common range of soils, milligram per kg is demonstrated here, and it is ranging from 10,000 to 300,000. So this is the limit. Similarly, we have all the other limits. So let's see about the chromium. uh, so selected average of soil mg per kg is 100 milligram per kg, while common range of soil for soils, we are having chromium starting from 1 to 1000. So similarly, if we are going to find some other parameters, you can observe the range in which is falling in this range. And if we are talking about mg per kg, last in our last lecture we talked about it. This is actually showing us the concentration of solute present, which is attached or adsorbed with the solid particle of the soil, which is silt, clay or sand. And this is not the concentration of solute which is present in the aqueous phase, and that aqueous phase is in the pore volume, which is the in the pores, and it is demonstrating the volume present in the water phase. So that will be measured in as concentration milligrams per liter, but this one is the attached or absorbed uh, portion of that concentration of solute which has entered into the soil, and this is giving us the amount in solid measurements, which is milligram. So this milligram per kg of the soil sample, this is how we will be measuring it, demonstrating it. So metals associated with the aqueous phase of soil are subjected to movement with the soil water and may be transported through the vadose zone to groundwater. It is very obvious, and we have talked about it in the previous lecture. So metals uh, which will be present in the pores will be in the aqueous phase of soil, and these are more likely to be transferred to the uh, groundwaters if it is present in the pores of the soil. And metals, unlike the hazardous organics, cannot be degraded, and some metals such as chromium, arsenic, selenium and mercury and can be transformed to other oxidation states in soil, reducing their mobility and toxicity. We talked about this topic as well in the previous lecture when we talked about the different oxidation states of chromium. Chromium normally have two different oxidation states in which it will be existing. One of them is the hexavalent chromium, and second one is the trivalent chromium. Hexavalent chromium is actually showing the fresh contamination, acute contamination, while once it is reduced to trivalent chromium, then it will be represented as chronic contamination. So this is the contamination. Trivalent chromium is the contamination which can be found in the soil volumes, while the hexavalent chromium, it will be found in the pore volumes. So most likely in our drinking water we will be finding trihexavalent chromium, and that hexavalent chromium is coming freshly from the source. With the passage of time it will be transferred to the trivalent chromium, and that trivalent chromium has the ability to react with the clay particles, and it has the ability to sustain in the soil environment. So if the chromium is going to sustain in the environment, it will be shifted to the trivalent chromium, and then it will be getting adsorbed to the clay particles, because this chromium trivalent is having cationic characteristics, cationic property, and then it is going to react with the anionic clay charged negatively charged clay particles, and then this bond will be existing in the soil environment as long as it is being desorbed. So this is something about the role of different ionic conditions, oxidation states, and how it is going to affect the mobility and toxicity. So for example, if we talk about trivalent chromium, it is not as toxic as hexavalent chromium is. So hexavalent chromium being fresh and directly coming from the source is more uh, lethal. It has more toxic effects as compared to the reduced form of chromium, which is trivalent chromium. So if trivalent chromium is present in the soils, it is not as toxic as the hexavalent chromium is, and that hexavalent chromium will be present in the aqueous phase and the groundwater phase, and most probably it will be found in the groundwaters. So immobilization of metals by mechanisms of adsorption and precipitation will prevent movement of metals to the groundwater. So we have talked about it. And retention capacity and effect on mobility. So metal soil interact in such that when metals are introduced in at the soil surface, downward transportation does not occur to any great extent unless the metal retention capacity of the soil is overloaded, or metal interaction with the associated waste matrix enhances the mobility. So as long as the ions entering solutes entering into the soil has the ability to change their oxidation states, react with the available metals, react with the soil particles, it will be uh, uh, sustained, it will be retained in the soil samples unless and until their efficiency is it saturates, and it cannot have it does not have any more capacity to retain more solutes, then it will allow the particles to remain in the solute in the aqueous phase to pass on to the groundwaters. Similarly, so fate of the metals in the soil, these will be having these properties. So dissolved in the soil solution, occupying exchange sites on inorganic soil constituents, specifically adsorbed on the inorganic soil constituents associated with insoluble soil organic matters, precipitated as pure or mixed solids, present in the structure of secondary minerals and or present in the structure of the primary minerals. Understanding of soil, water and metal chemistry is important for application of the remediation techniques. So these are the possibilities which we have talked. So we must understand the behavior of of the solute so that we can have a desorption option. So desorption mechanism will be only based if we know the properties of their solute and the properties of that soil volume. So soil properties affecting adsorption. Adsorption of metal cation have been correlated with such soil properties as pH, redox potential, clay, soil, organic matters, iron, uh, and manganese oxides, calcium carbonate contents, anions, adsorption has been correlated with iron and manganese oxide contents and pH and redox potentials. Adsorption process are affected by these various soil factors by the form of the metals added to the soil and the solvent introduced along with the metals. So let's talk about the chromium in soil and its behavior. Chromium exists in two possible states, trivalent and hexavalent. So forms of hexavalent in soil are like this HCrO4, which predominates at pH less than 6.5, or this CrO4, which predominates at pH 6.5, or and as a dichromate, uh, which predominates at higher concentrations, more than 10 milli mm, and at the pH 2 to 6, the dichromate ions pose a greater health hazard than chromate ions. Both hexavalent ions and are more toxic than chromium ions. Review of the process that controls the fate of chromium in soil and the effect these processes have on remediation are given in these references. So coming to the point, I think we have talked about the behavior of chromium in soil and its uh, different oxidation states. So hexavalent chromium was found to be only metal uh, that has highly mobile in alkaline soils. So parameters that correlated with hexavalent chromium immobilization in the soils were free iron oxides, total manganese, soil pH, whereas the soil properties, cation exchange capacity, surface area had no significant influence on the chromium mobility. So trivalent is readily absorbed on by the soils. So I think we talked about it. So these are some of the further findings which you can go through. Now we will talk about the sources which are actually producing the sources of contamination, and then how we will be classifying the waste. And I think it's again quite uh, understandable. This is the definition of waste, and which is the material not prime product, and for which the generator has no further use in terms of next purpose, production, transformation or consumption. So it need to be disposed. So the residuals recycled or reused at the place of generation are excluded. So these are the solid waste in the form domestic, commercial, industrial, plastic, styrofoam, containers, bottles, cans, papers. These are the examples. Liquid waste or like domestic washings, chemicals, oils. So according to the EPA regulations, solid waste is any garbage or refuse, sludge from the wastewaters, other discarded materials, and then solid, semi-liquid, semi-solid phases. So biodegradable and non-biodegradable are the classifications. Hazardous and non-hazardous is the classification. So some classifications based on their origin and type, you can go through this, and then their impact is here. So I think you can go through it. Waste hierarchy. So most favored option, and then the least favored option is the disposal, energy recovery, recycling, reuse, minimization, and prevention. So most favored option is the prevention. So what is prevention? It is actually the uh, lesser production of waste. We have talked about these concepts in our cleaner production technology course as well. And so some of the waste and their possible options like recyclable, reusable, compostable, and then dilute and disperse, we have talked about it as well. I think you can go through on your own. Impact of waste on health, of course. So please go through these topics by yourself. And then the options of their disposal. So landfill is one of the options of disposing the waste, but what kind of waste will be preferred to be disposed in the landfills? It is that waste which has no further option, which is left to deal with that kind of waste. So all kinds of hazardous waste which is totally dangerous and has its health impact, which has no further degradation possibility, which has no further burning possibility. So such waste will have only one option left, and that is the landfill. Another option up for the landfill is those kind of waste which have already been reduced uh, uh, in their toxicity, and now they will be safely disposed in the landfills. So let's talk about landfills in uh, detail. When we are talking about landfills, these are not actually the dumping sites. Dumping sites are totally different, and our engineered landfills are different. So we need to have much more facilitated and controlled environment to dispose our hazardous waste in as a final disposal. So that's only possible if our landfills are engineered landfills. We will talk about it in detail. What are engineered landfills? What are their properties? How they will be designed? So let's compare them. The rubbish waste pit versus the landfill, which is much more cleaner and have uh, uh, a better look than the other dump sites. Modern sanitary landfills are carefully engineered structures designed to isolate garbage from the nearby water. So these are the sanitary landfills and their usage. How is a sanitary landfill made? You can observe the cavities are dug out of the ground, and then the walls are sealed with layers of clay and coated with plastic to prevent groundwater contamination from wastewater that accumulates. The liner, you can observe here the overlapping to prevent the seepage and the percolation. So are designed to stay dry inside except for the liquids from garbage and rainwater that trickles through. As water trickles through a landfill, it dissolves chemicals and other particles, creating a leachate. So, four critical elements, which are bottom liner, leachate collection system, gas recovery system, and natural hydrological setting. These are important things. So, this is how a cross section of a landfill will look like. The dirt, starting from the bottom, we will be having dirt beneath landfill, and then we will be having compacted soil, then a clay liner, then a plastic liner, and then gravel or sand layer. Leachate collection pipes will be there, and then a garbage layer. So this is how we will be collecting it. Then what is done with the leachate? The state-of-the-art system constructed at the bottom of the landfill has a special double liner to prevent leachate leakage, and the contained leachate will be collected through pipes and storage in the tanks, and then it will be treated in the wastewater treatment plant. So even though there are two liners that overlap to keep leachate from leaking out, there is always that slim chance. So to help protect the public, landfills are also designed with detection meters and monitoring wells. So groundwater protection, landfills first exist as rubbish pits with no protection from leachate. Getting then we moved forward to those landfills in which there was no more percolation into the soil, and then that's how we can prevent the contaminated contamination to transfer to the soil and then to groundwaters. So this is the closing of the landfill once has been filled up to its capacity, and then the garbage in the landfill site is mostly anaerobic without the oxygen and water needed to break down, so they will not have the possibility to decompose on their own. And then this is how it will take time to decompose, like plastics up to 200 to 400, and then yarn waste is the green waste, can be shredded and used as mulch or composted, and then paper and cardboard, which will be in this proportion present in our samples in our wastes. And this is metal, glass, food waste. All these are the different kinds of waste available. So top 10 landfill issues: leakage, water contamination, air emission, remediation of old toxins, and then old municipal landfills contain hazardous waste, location of old landfills needing remediation, landfill and cover, and so monitoring of closed landfill will not be kept up, detection of old trash, and so these are the important issues which will be talked about in our next lecture, in which we will be purely talking about the sanitary landfills and their designing. So actually what we are focusing now is the possibility of the soil contamination. Landfills are the most probable source of soil contamination, because all our dump sites are a major source of our soil contamination. If you observe from where the soil is getting contaminated, it can the majority of the cases will be from the dump sites or landfill sites. Second option is from the drains in our country, in the case of our country. And then thirdly is the agricultural source, which is contaminating our soils. So there are three major sources of contamination: soil contamination leading to the groundwater contamination, which need to be dealt. At the same time, while talking about the landfills, which is one of the most important features dealing with the environmental issues, we are more concerned with the proper designing of the landfills, which must contain the gas recovery system, which must contain a leachate collection system, which must contain a monitoring system for both gas emissions as well as the leachate being percolated down into the soil as well as the groundwater. So that's how we will uh, be dealing with our this landfill topic. Again, it's important because it is dealing with the soil contamination. So in the next lecture we will continue with the designing of the sanitary landfills, and then furthermore we will talk about the probability how it is going to be remediated. Thank you.